Hi everyone. In this lecture, we're looking at this pretty beautiful paper. Its title isn't polyglycine oligomerization on silica surfaces, but that's what it's talking about. Basically, how can glycine come together to form peptides under prebiotic conditions on silica surfaces? So, the official title of the paper is Emergence of Order and Origin of Life Scenarios on Mineral Surfaces, specifically looking at polyglycine chains on silica. So I want to give a little bit of background today on what they're looking at. Now, origin of life research is just looking at how life came to be. It's also called abiogenesis. And an interesting area of this is understanding that life today, when using catalysis, uses proteins, specifically enzymes. If we look at, this is a very generic reaction, but you have a bunch of molecules, you have an enzyme, you can couple them together with dehydration synthesis kind of action. But how did life do this before? How did life come together? Well, did life use proteins in early catalysis? That's what we want to look at. But it begs the question, where did these early proteins maybe come from? That's what we have to look at when we look at this kind of paper. Basically, how can amino acids come together to form proteins under prebiotic conditions? So what kind of research has already been done? Well, when we're talking specifically about the polymerization of peptides, of amino acids to form peptides, the leading hypothesis is wet-dry cycling. So you have a bunch of amino acid residues, they come together and form a small oligopeptide. And to do this, you invoke high temperatures, you have a clay surface, and what you're going to do is you're going to induce an aqueous environment, then you're going to take that aqueous environment away, and you're going to cycle that many times, and you get oligopeptides. A paper by Campbell, they looked at glycine oligomerization, kind of similar to what we're looking at today, using wet-dry cycling, and you can see they got up in 10 cycles, they got glycine oligomers of 11 in length. So kind of interesting stuff when you look at this hypothesis and this model. But there are some limitations. It doesn't really take into consideration irregular wet-dry conditions. Like, for example, if this was done on a hot spring, like some think, okay, what if it rains and floods the area? That's going to induce some issues of like degradation. It's going to increase the rate of hydrolysis, or not. Sorry, I shouldn't say the rate of hydrolysis, but the ability to do hydrolysis, unlike when it is in dry conditions. You might also get weird side products and side chain reactivity in water with all those amino acids in the soup of amino acids. So that's also not a great thing with wet-dry cycling, although it is mediated by some mineral surfaces. So what are the authors doing about this? Well, they're going to make a new method. And this one, basically, you can think about it as if you were at a volcano and you had gaseous amino acids adhering to dry mineral surfaces. And what they specifically looked at to model this is using this idea of CVD, which is chemical vapor deposition, where you have these gaseous molecules come in, they adhere to the surface, they're going to react and form polymers, and that's it. So that's just an alternative to the wet-dry cycling method, where you don't have any problems like you would with water-based models. Okay, so what specifically was their method? Well, they took gaseous glycine, they put it at 160 C into this heated CVD chamber, and it's going to react and form these oligopeptides, as we'll see. And then you also have an outlet valve to sample collection. And the way that they collected samples, this is kind of important. They used formic acid as a chelating agent to get the adhered polymers to release themselves from the silica surface. So they used formic acid to do this. And the formic acid basically swaps places with the oligomer, and it's going to let it go out of the outlet valve to sample collection. So they ran two groups. They ran with formic acid and without formic acid, and the reason for this is just to see confounding variables, and also what good is a peptide that adheres to the surface and won't jump off of it to react. Okay, because that can be an issue. Usually, bigger peptides might have two 2 points of chelation to that silica surface, and that's an issue. We want these. We would want those oligopeptides to be on their own, but not on the surface themselves, and that's why formic acid was used in this study. Now, they used two detection methods. They used IR spectroscopy. This is going to tell you what kind of structures you have. They specifically are going to find beta sheets in there, but we'll get to that. And they also use mass spec. This is to determine the mass of the stuff or the oligopeptides coming through. So are you getting 5 residues long? Or are you getting 20 residues long? That's why mass spec was used. So let's just get to their results. Using IR, they were able to determine a mechanism that glycine is going to form beta sheets under these conditions. So if we look at this figure here, you have the silica surface. You're going to have adherence of glycine. Those glycines are going to react with each other to form these things called beta turns. The beta turns, you're also going to get these long linear chains forming while beta turns are being formed. One of those chains will bind on to the beta turn, and then the beta turn hooks on the other long linear chain of glycine, and you get these glycine beta sheets. Now, while the mechanism is helpful using the IR, they also found the overall sizes of peptides they were finding in. If they didn't use formic acid, it would be 11 residues long. So the maximum peptide length that is being taken off the CVD or the silica surface without formic acid was only 11 residues long. So not very big compared to 20 residues long when formic acid was used. So it kind of shows the importance of formic acid, and it's a pretty simple molecule. Formic acid's very, very easy. So it's a very important molecule. It shows its importance with these silica surface chemistries. Now, you'll also see formic acid used in the Formose reaction, specifically formaldehyde. So not quite formic acid, but I'm sure you can change it pretty easy. And again, that formic acid is very helpful. It's a chelating agent. It frees the peptides from the surface. So two kind of tidbits of information. We're getting these oligopeptides, but that formic acid is helping chelate it when it's done. So summary of kind of the research that was done here. The wet-dry cycling method is plausible, but it has kind of demanding conditions, and it opens the door for degradation. However, the authors propose a new method, a more viable method, CVD polymerization on silica surfaces at high temperatures. And I just want to reiterate, this might be, for example, in a volcano. Pumice, for example, has that silica nature to it. So you can imagine a volcano spitting pumice out of it, and you have these gaseous glycine molecules heated up by the environment. They might come to the site and bind on. That could be an example of an application in the prebiotic world of this chemistry. CVD polymerization also isn't the only method that has been shown. We see analog synthesis. This is complex chemistry that is occurring not with amino acids, it's with other stuff. It's very similar to peptides, but it just undergoes different chemistry to get to, like, dipeptides, for example. And there's other methods out there too that you can, like pyrolysis, I believe it's called. That one's cool. You like bomb it with heat. So a lot of methods out there. CVD polymerization is just adding one on, making a more viable method to avoid water. So kind of cool research that we looked at, but there are some critiques that I have. I just want to know, okay, what about the other amino acid species? This is a big issue with origin of life chemistry. We see a lot of these studies for polymerization done with glycine, and the reason glycine is chosen, if we go back to what glycine looks like right here, it's a very simple amino acid. There's not going to be any side chain reactivity. It's going to react just how we want it to, because there's no R group on it coming off. However, if we take something like arginine, right, there's a carbocation center here if we look at the resonance structure, so I guess partially positive at this point here, if you can see my cursor. And that's kind of an issue, I can't lie, because, okay, you can show it with glycine, but can you show it with literally the other 20-something amino acids that we have? Even like cysteine would be really important to show. Cysteine is a very vital amino acid residue for folding. It's those sulfide bridges can be vital for some of that peptide folding. So that's important to show too. So again, that's my really big critique, is we need to be showing the other amino acids. And honestly, I think it's grounds for a new stem of research in itself, because I wasn't able to find any other CVD polymerization reactions on the internet using other ones. But another more niche kind of critique is I want to know how much, right? Quantification is pretty important here. If we go back to this table here, I want to know specifically how much of the 20 mer we're making, or the 11 mer we're making, or that kind of stuff, right? How much of each oligomer are we getting? Right, I want to know the most abundant oligomer, because at the end of the day, the chemistry that's happening, it's a whole other realm to show selection chemistry and chemical evolution, but it's important to get that baseline of, okay, are we making mere thousands of molecules of the 20 long residue chain, or are we making like a couple femtograms or picograms of it, and that's pretty important in the understanding of this kind of research. So hopefully that kind of makes sense. Specifically, they used high precision mass spec, and that can pick up mere femtograms of samples. So I just want to know how much. To be honest, they would have needed to add like a whole nother method, a whole other section of their report. It would have just taken too long, and I'm sure that it just wasn't viable with the research funding they have. But maybe looking at like another follow-up study would be, okay, make the beta sheets with CVD, quantify how much they have using, I would say you could probably do that with HPLC. Well, actually, I think that might be a little too big over the HPLC limit, but some sort of capillary electrophoresis could be one that we could do, that they could look at, for example, and that would help quantify. So here are my citations, just 3 of them: wet-dry cycling information, wet-dry cycling information, and then the paper itself listed in citation 3. So hopefully you guys enjoyed, and have a wonderful day. Bye-bye.